right, you guys, we are ready to learn our final transformations for graphing. So just to give you an overview, so far we have learned 3 types of graphs: square root function, the absolute value function, and the rational function. And at this point, I expect we all know how to graph those because we've been practicing them so much. Then we have learned a vertical and horizontal translation, which is side to side, up and down, a vertical and horizontal reflection, which is like up and down or right or left. And today we're going to finish it off by learning about stretches and compressions. I obviously saved the best and hardest one for last. So this lesson is probably going to be the most challenging transformation. If you're wondering what we're going to do tomorrow, we're going to put everything together and learn how to graph stuff with all of the transformations all together. We're also going to do that on Monday. We're not going to move on to any new unit. I feel like we need more practice. So Friday's class and Monday's class will just be graphing, and then you're going to have your quest on Tuesday. So let's get right into it. We're going to be, let's all say hello to the super cute fox. Now I have to point out the cute animals because you guys called me out when I didn't put them on. We're going to talk about a vertical stretch and a vertical compression. So first, I want to show you visually what that looks like. So just take a look up here. I imagine when I'm talking about a vertical stretch, I am holding my function from the top and the bottom, and I'm stretching it like this. So you're physically stretching it. It seems like our function is going to get narrower when that happens. And a compression, a vertical compression, is you're holding your function from the top and the bottom, and you're compressing it, and it seems like it's going to get wider. So that's sort of how I look at it visually. Where exactly can you find the numbers for a stretch or a compression? You can find, just like when we learned parabolas, you can find the number right in front of the f of x. So we call it the a value. And the important thing to remember is if that a value is a whole number, like 2, 3, 4, 5, that is going to be a vertical stretch. If that number is a fraction, and I'll try to stick to easy fractions, so a half, a quarter, a third, that is going to be a vertical compression. And I've written that down on the side over here. But also we're going to do so many questions, you will remember it by the end of today. Another thing I want to draw your attention to is anytime you have a number on the outside of the function, that refers to a vertical transformation of some sort. In this case, it's a stretch or a compression. And it's always going to affect your y value. So for your mapping coordinates, what's going to happen is if you have a number outside of the function, you are going to multiply that number to your y value in your mapping coordinates. So let's go ahead and try it. I have the same squiggly graph from the first day that we were doing this. I have already listed down all of the main points. So -3, 0, -1, 3, 2, -3, and 4, -1. I'll give you a second to write those down. And the first graph we're going to try to graph is y is equal to 2f of x. Okay, so let's analyze this. We have a number on the outside. That means it's going to be vertical. That means it's going to affect your y values. And because that number is a 2, is that going to be a stretch or a compression? Good, so that's going to be a vertical stretch. What does that look like for our mapping coordinates? It means our x values will stay the same, and every y value is now going to be multiplied by the number 2. So when we do that, we have -3, -1, 2, and 4 all stay the same. And then 0 times 2 is 0, 3 times 2 is 6, -3 times 2 is -6, -1 times 2 is -2. Our a value is just the number 2. It's whatever the number in the question is. And if we were describing this transformation, we would say, we kind of already wrote it up there, so I'll just repeat it here. It is a vertical stretch by a factor of 2. Actually, I don't need to charge this anymore. So hopefully you guys are using a ruler, and then it's going to be y is equal to 2 times f of x. And visually, you can see that our original graph was in the black ink. This graph is vertically stretched. It's like you're pulling it from the top and the bottom. That's what it looks like. Okay, let's now look at this, the other example. I'll just erase this so it doesn't get confusing. Let's take a look at the other example. So this time we're graphing y is equal to a half f of x. Again, let's break this down. I have a number outside of my function, which means it's going to affect my vertical, so your y value. And because it's a fraction of a half, is that a stretch or a compression? Good. So this is going to be a compression. That means visually what's going to happen is our graph is going to be compressed. So we should expect it to be like squished in this direction. And when we're doing our table of values, we are going to take all of our y values and multiply them by a half. So your x values will all stay the same. 0 times a half is 0. 3 times a half is 3 over 2, which is the same as 1 and a half. Negative 3 times a half is negative 1 and a half. Negative 1 times a half is negative a half. Whenever you're graphing, you guys, make sure your numbers are mixed fractions because it's too hard to graph 3 over 2. It's a lot easier to graph 1 and a half. So negative 1 and negative 1 and a half, 2 and negative 1 and a half, and 4 and negative a half. And also in today's class, we are going to be graphing a lot of fractions. And my advice to you for that is just try your best in terms of estimating where the fractions are. My A value in the question, you get it directly from the question, is a half. And we already talked about the words. We're going to call this a vertical compression. By a factor of a half. So what we're going to do now is I'm going to skip through the graph, this graph, this graph, and this graph. I'll come back to the solutions after when you guys actually start trying it. But go to the page that says horizontal stretch and compression. Let's learn what that is as well. Then you'll have lots of time to work. So you guys, in graphing, I consider anything horizontal to be the trickiest. And the reason why is anything horizontal, which affects your x value, is always the opposite. So do you remember when we were doing horizontal translation, if you had like a +3 in our mapping coordinates, we wrote -3? Remember how it was always the opposite sign? So again, for a horizontal stretch and compression, we're going to think of it as opposite. And I would say this is the hardest transformation. You really need to be thinking and concentrating when you do these types of questions. So let me break it down for you just like before, and then we'll try some examples. This is called your K value. So basically, anytime you have a number attached to your K or inside of the bracket, it refers to a horizontal stretch or compression. Now, in the gray, I have the rules written, but before we get into that, I actually want to show you why they are this way and what you would actually do. So again, I have the same squiggly lines. If you want, I'll give you a second to write down all of the coordinates. So the coordinates are -3, 0, -1, 3, 2, -3, and 4, -1. Okay, here's how I think about this. I look at my equation, I say, okay, we're trying to graph f of 2x. I recognize that this number is inside of the bracket, and anything inside of the bracket will affect my horizontal. And that means in the mapping coordinates, it's going to affect my x value. So vertical affects your y values, horizontal affects your x values. but I'm not going to think of it as a 2. I'm going to take the opposite of that. And all that means is you're going to take the reciprocal. So the number 2, you are going to change into a half. You are then going to use that number a half for your mapping coordinates, which means you're going to multiply your x value with a half. And you are going to use the half to describe your transformation. This means when I'm describing this transformation, I am going to call it a horizontal. And even though the original question has a 2, I'm not thinking of it as a 2, I'm thinking of it as a half, which means is it a compression or a stretch? If it's a fraction, compression is right. So this is going to be a horizontal compression by a factor of a half. Oh, it looks like a spider. I don't know what this is. Let me just do it one more time. Let me explain it one more time. I recognize that there is a 2 in my question. It's inside of the bracket. That means it affects my horizontal, which means it affects my x value in the mapping coordinates. However, everything that is inside the bracket is always opposite. The opposite of a 2, when you flip it, is a half. So I think of it as a half. And where do I use these numbers? I use them for my actual mapping coordinates. So I'm going to multiply my x with a half. And I use it when I'm doing my description. So a half is always a compression, which means it's going to be a horizontal compression by a factor of a half. Now, this is confusing, which is why I never really ask this question. I have it on the sheet, but I rarely ask it. I'm asking for what is the value of k, and it's a little bit annoying because what I'm really asking you is what is the actual value of k in the original question, which is a 2. But I never ask that question in assessment or anything. I'm just showing you that in the original question, your k value is a 2. The question doesn't change, but for everything else, we consider it to be a half. Bea? My answer for question. Okay, perfect. Let's go ahead and now do all the work. So -3 times a half is -1.5. -1 times a half is -1/2. 2 times a half is 1, and 4 times a half is 2. And your y values will not change. And remember what's happening with the horizontal compression. You're taking your graph side to side and you're squishing it like this. So you should expect your graph to be compressed like this. What am I doing? Sorry, 1, -3 and 2, -1. Did I do them all right? -1/2, 3, and then 1, 3. Yeah. And I'm going to call this y is equal to f of 2x. Is that okay? Did you guys get that as well? Okay, last example before you guys work on your own. Let's try this graph. Y is equal to f of 1/2 x. So again, I'm going to walk you through my reasoning. I'm going to show you exactly what I'm thinking when I see this. I see a number inside of the bracket attached to my x. That means that is something to do with my horizontal. It's going to affect my x value. I also know anything inside of the bracket that affects my horizontal has to be switched to the opposite. The opposite of 1/2 is just a whole number 2. Where am I going to use that 2? I'm going to use that 2 for my mapping coordinates. So I'm going to multiply my x with the 2. And I am going to use that 2 to describe the transformation. So if I'm describing the transformation, I'm going to say it is a horizontal what? Good. A horizontal stretch by a factor of 2. So what does that mean visually for the graph, you're holding your graph side to side, you're stretching it out. So it should be expanded like this. And the annoying part is, what is the actual value of K in your original question? That doesn't change. It's still going to be a half. Okay, so I'm just going to erase this stuff that I've made so messy. I'm going to multiply all my X values by 2. So it's going to be -6, -2, 4, and 8. And your Y values don't change. So -6, 0, -2, 3, 4, -3. It does go off the graph a little bit, but that just means that the graph is just being really, really stretched horizontally. And I would label this Y is equal to F of a half X. Any questions, immediate questions? Okay, so you're actually not going to be working completely on your own. It's going to be guided. You can work with whoever you want. I don't mind that, but I'll basically show you the question. I'm going to give you maybe 5 or 6 minutes. We'll take up the answer, and we'll do that for all of them, so that by the end of the class, you've done all the graphs and you're going home with like minimal homework. So go ahead and get started on, we're going to go back to vertical stretch and compression. We are going to, well, don't copy anything, just ignore the questions aren't there. I'm actually posting it for the virtual kids. But you're basically going to be graphing f of x is equal to the square root of x, so the original graph of square root. Then you're going to be graphing f of x is equal to 3 times root x. So remember, that is a vertical stretch. You're going to multiply your y value with the number 3. And then you're graphing f of x is equal to 1 over 3 root x, which means it's a vertical compression. You're going to be multiplying your y value with a third. You'll do all the math, you'll graph it, and then you'll look up and see if we get the same answer. Okay, so go ahead and get started on that. Yes. Okay, hello recording. So here is our vertical stretch and compressions for the square root function. So we have our square root function in black, the original one. Then when there's a number outside, like 3, that tells me that I'm multiplying my y values with 3. And when there's a third, I'm multiplying my y values with a third for this one. I graph them, and that's what they look like. Here it is for the absolute value function, the same concept. So you have 3 times the absolute value. So you're going to multiply your y values with 3. And then for the second graph, you have a third, which means you're going to multiply your y values with a third. And here's what the graphs look like. Do you guys still need the absolute value up, or can I show you the rational? Next. Okay. Here is what the rational function looks like. You guys, for the rational function, do you expect the horizontal and vertical asymptotes to move? For a stretch and a compression, should the asymptotes move? The answer is no. They only move for a translation, right? So for these graphs, your asymptotes will stay where they are because the graph is not moving side to side or up and down. Rahima? Oh, yeah. Yeah. But just when you're graphing it, your asymptotes don't move. They're going to be at x is equal to 0 and y is equal to 0. And that's what the graph looks like. All right, you guys, let's just take a look at the next set of graphs. These are our horizontal stretches and compressions. So what I did for the square root is, again, the left-hand table of values is my original. Now, see how it says square root 2x? That means I take the opposite of the 2, which is a half, and I multiply that to the x. So my mapping coordinates are a half x comma y. For the other graph, because I have a half inside the square root sign, I take the opposite of that and multiply it to my x. So it's going to be 2x. I got lazy with my transformations. Please don't use symbols like this. You have to write the whole words on an assessment. But basically, this is a horizontal compression by a factor of a half. This is a horizontal stretch by a factor of 2. So I'll leave this up for maybe 5 minutes. Try it, and then we'll do the absolute value one. Anything? here are the graphs for the absolute value. Again, I use 3 1/3. So for the table of values in the middle, if there's a 3 inside, I multiplied my x value by 1/3. And if there's a 3rd inside, I multiplied my x value with a 3. And this is what the graph looks like. All right, and the last graph, you guys, this is the rational function with a horizontal stretch and compression. Now, I've kind of shown you 2 different ways to write it. The second way I find is a little confusing, but I just wrote it there just so you can see that it can look many different ways. But basically, I like to consider it to be 1 over 4x or 1 over a quarter x. Just like before, if I have a 4 with the x, that means I am going to be multiplying my x values with a quarter. If I have a quarter with the x, I'm going to be multiplying my x values with the 4. And that's what the graph looks like. Goodbye, recording.